Thank you everyone for attending. So I'm going to talk about some of the research I've been doing on software security and reliability. So I'm gonna start by saying something that everybody should be aware by now that our world is kind of run by software these days. So software is not just living in our personal computers and our phones and the cloud, but now it's kind of running our various types of vehicles. It's surrounding our industry, our agriculture. It's in defense systems. It's in kind of IoT, which means could be anything from your water boiler or your coffee maker to whatever, right? So software is everywhere and is actually getting a lot bigger. So this kind of made the news recently because there was an article saying that a modern high-end car has like 100 million lines of code. I mean, that's a lot of code, right? So you can see this graph shows it's like almost double of all the code used to run Facebook. All right, so this is just the code running in a high-end car. Now the problem is with more code come more problems. So the bigger the software is, there's been many studies showing that with more code and more complexity, the number of bugs in the code is actually also increasing, right? And by bugs, we're referring to essentially faults, errors that were done by developers, and they can cause kind of a variety of issues, like but uh, essentially they give you kind of unexpected results, right? Or the program does not work in the intended way, right? And wherever we have bugs, we also have vulnerabilities. So what are vulnerabilities? Essentially, vulnerabilities are some bugs that can be, let's say, uh, repeatedly and with high confidence rate triggered by attackers. So by people that want to trigger them to, let's say, reduce the security of some piece of software and cause harm. And what harm means is, the simplest thing is you can imagine it as reducing the availability of software, right? So crashing a server, making your car not start. That's kind of like one of the cases, right? In, let's say, the worst case scenario is where an attacker can actually gain unauthorized access to your software and your system, and that also means your data, right? So they can use your system to obtain access to your data, or they can use it to run arbitrary computations, right? And again, as we cross in the physical realm, they can get access to physical stuff, right? So they can start controlling your car and stuff like that. So vulnerabilities are bad, and kind of discovering and exploiting them is kind of big business these days. So it's a big research area in both industry, academia, but also kind of in business, right? So the government is doing it, crime syndicates is doing it. Everybody's trying to essentially find this kind of vulnerabilities and generate exploits that will allow them to launch attacks to gain data or gain unauthorized access. And it's a very lucrative business, right? So if we look, let's say, at the what we call the white hats, like the good guys, right? There's huge competitions offering like a lot of money to people that demonstrate this kind of vulnerabilities and exploits. And the goal, of course, is that these are kind of they can be eventually fixed by the vendors, right? And similarly, the vendors themselves have stuff called like bug bounties, where essentially if you submit a bug you found, they will offer a price for you. Right? On the other hand, there's also what we call like black hats, right? So people that do this for a living, but they want to get more, let's say, money. So selling this kind of vulnerabilities and exploits is especially what we call zero-day exploits, like previously unknown attacks, right? That nobody would have heard of before. They go like for hundreds of thousands of dollars. So this is kind of big business, right? So the security of this kind of software has become really big business. And the impact of this is quite huge in terms of financial damage. So if you actually Google, you'll find a lot of different sites giving you a different number. I picked this one. Is kind of, it seems very kind of trustworthy and a very big number, like $600 billion and counting. This is kind of the annual cost of uh, kind of security incidents. But it's not only limited to kind of financial damage, right? So as software is now in more systems that we use kind of from everyday activities to warfare or kind of like flying around the world. Let's say we have issues when security problems appear in such systems, like we kind of have national security issues, and these are kind of, you see a couple of articles showcasing uh, the good guys actually trying to find these faults before some other entity does. And of course the government is aware of this, right? There've been like significant investments in cybersecurity, and this of course does not include only research, right? So there's like $15 billion where let's say dedicated to cybersecurity related activities in fiscal year 2019. This keeps going up, but of course it involves like anything you can imagine, right? But this is just to show that this is kind of an important issue that keeps getting more and more critical. Right? So what I've been involved with is part of my research has to do with kind of improving the security and reliability of software, and specifically, I've been looking at software that has been developed in C and C++, and these are kind of two programming languages. And there's kind of three, let's say, vectors, three kind of directions I've been looking at. So the first is what we also call offensive security, right? So we try to discover novel ways of attacking and exploiting software. And this may seem counterintuitive. How can you improve the security by attacking? But this is actually a necessary step, because this is a way where we kind of get to evaluate some of the stuff we develop or the industry develops. So we identify the problems before they're actually being exploited in the real world, right? So this is kind of important for us to test what we're doing and kind of push security forward, right? Then, of course, we have what somebody would expect, right? So we have kind of we develop systems that that prevent the exploitation of vulnerabilities, and some of them can be like, let's say, generic and can have kind of apply to different kinds of software, but usually they are kind of very software and vulnerability specific. And finally, we have kind of a third direction, which is where we kind of focus on developing techniques that harden exploitation, right? So in many cases, it is sufficient to try to make exploitation of a vulnerability really hard for attackers, because it is kind of a game where somebody has to kind of, let's say, balance the time investment and the financial investment in something and what they can get out of it. So by making it basically very expensive for attackers, we actually get some gain there. And sometimes it's kind of the only way we can get something practical that can be deployed in real life. So I mentioned that I've been focusing on C and C++, and I don't know if anybody in the audience is kind of working with different systems and different environments and different languages. So these kind of languages are pretty old. Their main characteristic is that you develop the software in this language, and then you go through kind of a compilation process where you turn this your program that you develop into binary software, right? And binary software is essentially it's a piece of software that is encoded in the language that the processor understands. So that we say we executes directly on the processor, right? It runs on the metal, as we say. So because of this, it has actually some significant benefits, right? So first of all, it's very performant and also consumes the least energy, let's say, compared with other languages. And the constructs the languages offer kind of map efficiently with the hardware, right? So when you actually want to do things that talk to the hardware, this is kind of the most efficient way to do so. As a result, this is used by a lot of what we call like system software, right? So your browsers, your network servers, your operating systems, a bunch of stuff your other high-level languages are using. All of them are kind of using a part that is developed in this language. Now, the problem is that these are actually languages that are very error-prone, right? They push too much responsibility to the developers, and as such, it's very easy to make mistakes. And any vulnerabilities you get here kind of lead to the worst kind of exploits. You get like arbitrary code execution. The third party can basically completely control that program that it just attacked. So in the rest of my talk, I'm gonna especially focus on the third direction I mentioned earlier. So how do we harden exploitation? And specifically, I'm gonna talk about binary software. So this is software that's been developed in C++, compiled, and you have a kind of a binary version of it, right? And this kind of includes a lot of proprietary software, right? That you don't have the source code for, or maybe software that is old and you've lost the code. And this kind of very big problem in the government and in the industry. So the work we've been looking at tries to exploit this kind of observation that software is bloated, right? So there was a research done on Android applications saying that, you know, whenever somebody develops an application, their application is actually a small part of the whole code being used. Like they use a lot of libraries, which is essentially, you know, you could say third-party code or code that is there to kind of facilitate development. So even though if you add a small application, you end up including kind of a huge amount of code that is included because of libraries and other things. So the question here is, so this kind of code, which may not even be used, creates bloat. Can we actually, do we gain something in security-wise? Can we harden exploitation by eliminating this kind of bloat in software? So what we do, we have a project now where we're looking at kind of bloat in different kind of, let's say, different types of bloat. So we have, for instance, the most straightforward is when you have an application, it uses libraries. All these libraries are loaded by the application. But you know, even if you use just a single function from that library, the whole library is actually included in the application, right? So we have unused library code, and that actually can be bad, right? So first of all, we know that this unused code, even though it's not used by the application, it can be used by attackers. And this is because of a new technique that is being used now. It's called like code reuse. And the idea is that the attackers chain existing code fragments to create a new program that implements their kind of arbitrary malicious functionality, right? So you can consider this like a newspaper, and somebody's kind of constructing this kind of ransom note. So where you pick available letters and you combine them into a completely new sentence, right? So this is kind of a technique used by the attackers. So unused library code facilitates that. But not only that, it actually also makes the life of the defenders a little bit harder, because you can have defenses that take the whole application and the library and they try to defend against attacks. And essentially, you may be forcing the defense to kind of protect code that is never used. And that kind of usually leads to higher overhead, which ends up a kind of, let's say, disadvantaging the defender. So what we did is we kind of started building systems that try to eliminate the bloat. So one of the first systems we did focused on kind of eliminating unused code in libraries. And the goal was to essentially generate libraries that have this kind of unused code removed, right? So we use a set of analyses that have to work with binary code. So it's actually quite tricky to, first extract the binary code and reconstruct stuff like the function call graph and control flow graph of the program. So we actually used metadata available in modern systems to do that. And we built like a prototype that works with modern Linux binaries. And we tested with a popular operating system. And what we got from there is essentially we see that if we combine together, we took a couple of servers and benchmarks and some basic utilities, and we look at all of them, we see that the libraries they're using, basically about 50% of the code in those libraries is never used, right? If we look at the functionality in the terms of APIs or functions there, this is about 73%, right? So indeed, even kind of in binary systems, we see like there is a lot of bloat that basically only disadvantages defenders. Now, we're taking this idea to kind of different kinds of bloat. So another idea is, another bloat issue here is that your unused code is using kernel interfaces, right? So operating system interfaces. This is how you get to do anything useful if you are a program. And These interfaces are very critical because they allow you to, they can be used to attack the operating system, and they can be used to do, useful stuff for the attacker. So by eliminating them, by, removing stuff that are not needed, we also kind of limit sandbox what attackers do when, or if they exploit the application, right? So again, what we do, we employ kind of various analysis there to try to identify which system calls exactly are being used, and then we use kind of existing filtering mechanisms to block that. All right, and if we look at a huge distribution, we see that indeed, like there's a huge percentage of applications that actually do not use, like not even half of the system calls available on modern systems. And it's in direction where we try to improve this further is we're going to try to introduce time into the mix here, right? So applications do not use all system calls all the time. Specifically, an application can be easily split into these 3 stages, right? Initialization, the main functionality, and some cleanup code. So we can actually, if we can identify this automatically, then what we can do is we can kind of create more fine-grained filters that, you can filter the system calls needed at the entire application lifetime, or just after initialization, you can kind of then provide a stricter sandbox that further restricts the application only for the code required to run its main functionality. Again, I understand I'm running out of time, so this is kind of the last thing I want to talk about very quickly. So the last, let's say, source of bloat is that you actually may have functionality that is included in the application, right? You can use it, but in reality, it's actually unwanted, right? And this is kind of quite problematic because you may have an application that includes hundreds of features that you don't need, but if there is a vulnerability in some of these features, even though you don't use it, an attacker could potentially trigger that code and exploit your application, right? So what we're looking at is finding ways to remove this functionality. And again, we combine various techniques that have to do with static and dynamic analysis. And the interesting thing here, in my opinion, is that not only we try to stop the use of that feature, but we also try to see how can we allow the application to continue executing if that disabled feature executes, right? So the trivial thing to do would be to just terminate the application if somebody tries to use a disabled feature, but that would be very bad for servers that they have to restart, so it kind of reduces reliability and availability, right? So I'm not going to talk about this any further. Instead, I'm just going to kind of close my talk saying, software security is kind of an area that has become really critical over time, and it's becoming more critical just because we have more software in more places. We have a lot of old problems that they're still with us, unfortunately, and effective solution really kind of demands solutions that kind of cross-cut many areas, both in kind of computer science, but also kind of in other areas potentially. And it's a very hard problem, especially the kind of low-level security stuff we're looking at, requires people that have kind of a very good understanding of how these systems work. And of course, there's kind of the eternal issue of, balancing security and performance, right? Nobody wants to have very strict security with very bad performance. That doesn't help everyone. So this is kind of the end for me. I'm happy to take any questions if there is time. I understand.
Sure. Thanks, George. Questions from the audience? We can take 1 or 2 questions. If not, George, let me ask a question. And this is enormously important work, right? Software security and reliability. I think the Boeing 737 MAX, it's a very classic, maybe a textbook example about how important the software reliability is, and let alone software security. So my question is, how would the quantum computing concept, right, that certainly is being explored, fundamentally change the way we deal with the very issues that you've talked about?
So this is actually interesting because it's completely orthogonal, right? So quantum computing can solve like very specific issues that have to do with computation, right? But kind of general purpose computation, like you would have with a server just delivering your files. This is not something quantum computation can help you with. It can help you maybe compress these files or encrypt these files very efficiently, but you still have all these kind of components, what I call like the plumbing of your computer, right? So it may end up in a very nice place, which has a quantum computer, but to get there, you need everything else to work correctly. And actually, we had issues where even though the math was correct and everything should be fine, some other some mechanism was not implemented properly, and you had like serious security issues. So these are kind of completely orthogonal, I think.